Thank you, Irka. Good afternoon, everybody. Yes, I come from the Astronomical Institute, from very tiny working group, Planetary Systems. I speak on behalf of my colleague Aleš Bezděk and few other colleagues, a bit retired, but so we are a very tiny group right now. And my goal is to introduce you satellite gravimetry. Of course, the topic itself consists of a lot of activities we are working on, like the orbits, accelerometry, geopotential field modeling. But I think all these topics meet in satellite gravimetry. That's why I would like to provide you a general picture what satellite gravimetry is, what it brings, what is the perspective, and the current status. So what it is. Jakub from Mathematical Physical faculty introduced some geophysical topics. I would say that satellite gravimetry contributes also to these topics, like the geopotential field modeling, but basically satellite gravimetry is a field or discipline that tries to observe gravity field of the planets or planetary bodies with spacecraft. And there are, of course, a lot of different methods how to do that. The oldest ones go back to Sputnik, because since you have very accurate, or at least reasonably accurate orbit, you can do the inversion of the orbit and you can decipher some gravitational source, because the orbit is driven by the gravitational field. Of course, there was a development, and since 2000 we are talking about the decade of geopotential field modeling. It's not only gravity, but also magnetic field, as Jakub introduced. But for gravity field perspective, we have 3 spacecraft or 3 missions. In 2000 it was CHAMP, in 2002 GRACE, and in 2009 it was GOCE, it's pronounced Italian. And all these methods basically rely on very good positioning, because since CHAMP we have GNSS receivers, at the time it was GPS receivers, and with very accurate orbit, provided independently, we can stick to the geometrical modeling or the inversion of the geometrical orbits and to provide gravity field snapshots. Of course, the time developed, and in 2002 the concept of SST low, it's the middle picture. No, sorry. So you have 2 satellites. Each of them is equipped with the accelerometer that measures non-gravitational forces, so you can clean up all the measurements from what we are not trying to analyze, non-gravitational signal. And between the spacecraft, you measure the distance. The distance between the spacecraft is 200 kilometers, and we, or the missions operators, measure such distance at the micrometer accuracy, and now recently with GRACE follow-on, even with few tens nanometers. So 200 kilometers, very accurate measurements of the distance and its change in time. The change in time with time is important because we also study gravity field in a time perspective, as a time series. This concept of SST low was even more somehow novelized, and instead of one arm along the track of the satellites, constructors of GOCE put a lot of different arms, and they build up a gradiometer. This is a set of 3 arms, and each arm measures differential acceleration. So satellite experience some forces. These forces contain gravitational part and non-gravitational part. We can get rid of the non-gravitational part, and the residual between the red boxes here in each axis, along each axis, provides the gravitational signal with respect to that axis. That's history and present. And why? What it brings? You maybe will be surprised that even though that such building respects gravity, the gravity is everywhere, because gravity somehow leaks into the Czech law. Czech law defines reference systems. Each reference system must define also the vertical component of the coordinates, and the vertical components of the coordinate system is somehow related to geoids or quasi-geoids, as shown in this figure. So geoid is some surface, physical surface, that is very close to the ocean surface. It's equipotential surface, so the gravitational potential is constant on the geoid, or gravity, it depends. And with such surfaces, you can define and build up large tunnels, sewer system, and define all the settings here around us. So this is how it links to the society, the gravity. Of course, gravity and geoid is not linked only to the society and to the industry, but also to science, as Jakob already presented. And if you have geoid very accurately measured, the static gravity field, then you can look for the residuals with the actual or mean ocean level, and you can end up with the study of the currents, with the static or steric currents around the globe. The geoid itself, as you can see from the blue dip, somehow is related to the mass anomalies within the Earth. And so that's why geoid is also some geophysical snapshot of what is below us. And the smoother the signal is, the deeper source is, which means that the geoid can be used to constrain studies of the mantle or the lithosphere. And if you look not only on the geoid, which is zero derivative of the potential, but also on the first derivative of the potential, the signal looks a bit more scary, but it means that the response of the signal is rated to something shallower. So the higher the derivative of the potential fields sensed by satellites, the shallower structures you have. So you can study also the upper shallow structures or constrain such models like from seismology. The second part, or the second application of time, of gravity field or gravitational field, is its time variable part. Why? Gravity, as you basically know, reflects the masses. So if the masses globally change its position or they change in time, it means you have a way to observe such changes. And because present times is full of climate global changes, then you can ask if there is some footprint in gravity. And of course there is a footprint of gravity, and it also leaked the possibility to study global changes with gravity, also leaked to the international organizations like United Nations and World Meteorological Organization. And gravity, in terms of different words like groundwater volume or storage change, leaked among the essential climate variables. This is the set of variables that are monitored by global scientific communities to study the fragility and the climate system as a whole. What is shown on the picture on the right is a composite figure of different outcome from the gravity monitoring of the Earth. So for example, if you look at the Greenland or Antarctica, you can see large trends. So we are systematically losing ice or ice sheet in the north, also in the south. You can also see that there is some surplus signal coming from the Antarctica. So the story of the Antarctica is not that trivial. But at the end, the trends are clear. We are losing, so we are heating up the planet. Among the other things that we can see with gravity data is, for example, large droughts, large-scale droughts, like in California. It looks tiny here, but if you look at the area of California, you will see it's a quite big one. The same Middle East, where the deep water is pumped up and used for irrigation and so on. The disadvantage of gravity field sensing of such changes is the resolution. We have spatial resolution around 300 kilometers. That's not good. So this is basically a high-resolution picture from gravity you can find from all the missions. And the time resolution is about 1 month. So you obtain such a global map only by collecting 30 days of gravity data that are sampled with 1 or 2 seconds. So you have a lot of data and you obtain just one figure at the end. But still, such snapshots, such monthlies are very important if you have such monthlies for decades or 2 or 3 decades, because then you can reliably say what is the trend in Greenland, in the Antarctica, and so on. So, what is the present? The present status is GRACE follow-on, is the set of two satellites that measure the distance, as I explained. It works quite successfully. There are some issues, and because because of these issues, the international community like ESA, NASA, and DLR, they hurry up to build up a new mission that would be pretty the same like GRACE. So in 2027, it should be first pair of such satellites launched, just to replace GRACE follow-on if not working. And if the pair 1 will be successful, then later on, a couple of years later, ESA plans to develop also the second pair. It will be even lower at 400 kilometers, more inclined orbits, and altogether they will provide, and hopefully, we hope, all the community hopes, that we overcome the limitation of 30 days and 300 kilometers in spatial domain. So we can maybe come up with 2 weeks fields and 2 or 100 kilometers spatial resolution. That would be good enough even to study the Czech Republic itself. Thank you very much.
Thank you very much. Time for a quick question, if there is. Yes?
You have mentioned that you will get some data because you can spam it for a few decades.
Yep.
But during this time, there is a development, and how do you guarantee that your detectors will work for such time? That you will keep precision. That everything will stay for 3-4 decades.
It's up to the agencies that develop the instruments. But for example, GRACE, the first GRACE pair mission, it was designed to work maybe 5 years, and at the end it worked 15 years. So we hope that they will basically copy the things that were on GRACE, and they add maybe some refinements like laser interferometer to improve the accuracy. But I don't know, we hope. I think this is the space business. We all hope that it will work.
So thank you, Josef, again.